Okay. Yesterday we started talking about the atmosphere. Fiona, you'll have a worksheet to read and then do some questions on, okay? And we learned that there are how many layers to the atmosphere? Zico? 5. Starting closest to the Earth, they are the troposphere, stratosphere, mesosphere. Meso means middle, thermosphere, and exosphere, outer layer. Okay?
Your plate is really good.
All right, so today we're going to dig in and talk a little bit deeper about the functions of the atmosphere. The atmosphere's purpose is to do what?
Keep us
Protect us. Thank you. That was the big takeaway. Miss Watson wanted us to have. Miss Watson popped in this morning and randomly started asking atmosphere questions. And so the big thing that the atmosphere does is protect the Earth. That article yesterday said it wraps us up like we're in a blanket, right? Hang on a second. So it protects us in 3 different ways. It protects us from harmful UV rays. It helps us, what else?
from meteors.
All right, asteroids and meteors and everything burn up in the, what else, Fiona?
It helps with oxygen and heat, and like in the summertime, sometimes it's cold.
Okay, so it holds in the heat so that we don't get too cold, and it's where our oxygen is. It's what allows us to breathe, okay?
If we
So-
don't have any atmosphere, we float up into space.
No, that's gravity. That's different.
Oh yeah, that's gravity.
That's different. Okay, so it has the atmosphere. Hang on, let's rewind because somebody else wrote something about this yesterday. Atmosphere has nothing to do with gravity. Okay, gravity we're going to talk about later, but that's at the core of the Earth. That's not atmosphere. Atmosphere has 3 major functions, and all of them protect us in some way. Protect us from the harmful UV rays from the sun. Help protect us by keeping us warm, and gives us oxygen. Okay, protects life as we know it on Earth. So we talked about that that the atmosphere helps keep us warm, but how? Okay, so that's where we're going to go on page 364. On the first day of spring, the thermometer outside your window, if you are in New York City, reads 41 degrees Fahrenheit. Your friend lives in Miami, Florida, which is about, I'm just going to say miles because that's what we know, 1,290 miles to the south. She says the temperature there is 72. What causes the temperature to be warmer in Miami than New York City? So if we think about the map of the United States, New York is in the northeast, Florida, Miami, Florida is in the southeast. Jason, what do you know that could tell us why is it warmer in Florida than in New York on the same day of the year?
It's warmer because it's closer to the sun.
It's closer to the sun?
It's closer to the equator.
Closer to the equator, which is technically closer to the sun. Because if you remember from when we did our space unit, if this is the sun, during the summer, we're tilted towards it. During the winter, we rotate around, we're tilted away from it, right? So, but if you're further south, then you're that much closer to where the sun is hitting the earth. So let's keep reading. When sunlight shines on Earth, energy from the sun warms Earth's surface. The solar energy that reaches a planet is called insolation. How many of you have heard of insolation like at your house?
Yeah.
Like your parents have talked about insulation at your house or
Is that
whatever.
like this pink stuff?
It's like some pink fuzzy looking stuff. Sometimes it's white.
Yeah, when you touch it, you get really itchy.
And it's really itchy because it's actually teensy pieces of microscopic glass that has in it. But it's called fiberglass. And it's like glass that's been spun into really thin pieces of fibers. And it was it's in between the walls. So in between the outside wall and the inside wall of your house, you have this stuff called insulation. And it's what holds the heat in the winter and keeps it cool in the summer.
Okay. Connection with that. So there's this really big house in our neighborhood, and it's like a mansion. You could call it a mansion, but it like people used to live there, and then it got struck by lightning, and it like messed up all the insulation, and then it got abandoned. But someone bought it and lives in it now.
Oh, okay.
I
All right, so hang on.
Grass.
Grace, hand raise.
There's insulation in the walls of our cheer building, but like if you accidentally like kick or punch the wall, it's not like a hard wall, but you can like kick or punch through it, and then you can like see all the insulation.
Oh yeah. Turn it up from
Yeah.
here.
Don't hurt your hand punching the wall though. Goodness.
My sister
That made me.
My dad punched through a wall.
That's crazy. Okay. So yeah, if you get mad and punch a wall and punch through the drywall outer portion, you will see the insulation underneath it. Bad idea to punch your wall out. Let's not do that. Okay. One reason for the difference in temperature is Earth's shape. Earth is shaped like a sphere. We know that. An imaginary line called the equator runs around the middle. We know that. Sunlight strikes with the most vertical angle at or near the equator.
90 degrees.
At 90 degrees-ish, yes. Which is like, we know 90 degrees is exactly perpendicular, okay? If you think of the sunlight as a beam of light, the beam shines on Earth in a circle at the equator. So the sun is hitting the equator exactly like this, at the equator. But if you go north of the equator towards us, towards the United States, where the Earth starts to round around, right? So now the sun is hitting at an angle. It's not hitting it directly, it's hitting it at an angle, okay? So it's not as strong. Does that make sense? If I hit something dead on versus I hit it like this, it's going to hurt more if I hit it flat dead on than if I am allowed to kind of slide off. Does that make sense? Okay. So when the sun's rays are hitting us, because we're not right at the equator, we're up north where it's rounded a little bit. So the sun's rays are hitting us indirectly. Okay. And same thing if you're on the south end, the sun is hitting this way, southern hemisphere, right? So
we're hitting
the beam of sunlight always has the same amount of energy. However, the oval, if it hits it directly at the center, it's one little circle of light that it needs to warm, right? But if it hits here, think about that reflection of the sun. It's going to cover a wider space. And you see those pictures at the bottom of page 365 that kind of show that it's like the flashlight on a board. If the board is at an angle, it turns into a big oval instead of just a little circle. And then the sun has to heat that big oval area instead of just the little circle. And so some of that energy and that heat energy is spread out. It's not as warm. Okay. So does that kind of make sense? I can probably try and reenact that thing that's in the book. Turn light off. Yes, quickly. All right, so I've got my flashlight. What can I use? I'm going to use something black. Sophie's Chromebook. All right, let's see if this works.
Can you pin yourself where we can see? You need like a flashlight that's direct, not one
Like,
that's
but yeah, this one's like the beam is too big. Hang on, let me pin myself so everybody can see.
Then it'll just light it up.
All right, so if I put my phone really close, you see it's like at a circle, and I'm holding my phone completely straight on. So it's hitting at a 90-degree angle, right? And I know you guys can't see it directly, but you can mostly see that it's in a circle behind my phone.
Yeah.
And if I tilt the Chromebook, do you see how big that area is getting compared to what it was now? 90 degrees. And now as I tilt it back, it's got a lot bigger area that it needs to warm. And so that heat energy is spread out. And so each little area isn't getting as much heat. But here, the heat is more concentrated. Does that make sense? How that works? Okay, so this is a flat object, but the Earth is more round. Okay.
Use it on the globe. Use it on the globe.
I don't know if it'll work on the globe. I can try it. All right, so the sun's rays right at the equator look like the circle, right? And then as I move up, oh yeah, that did work. Do you see how it gets bigger? So here's right at the equator. I've got a small circle. And as I go up, you see how that circle got bigger? It has to heat a larger, and the higher up I go, it gets even bigger.
That's cool.
So does that kind of help illustrate that a little bit, why the sun's energy gets spread out so it's not as warm, okay? So the areas that are farther north or south don't get as direct energy from the sun. It's more spread out, so it's not as warm there. So the closer to the equator you are, the warmer your climate is always going to be. Lights back on.
Miss Fab, I have a question.
Yeah.
So you know how so I'm thinking about the Antarctica, the top of the Earth where it's really cold, like the very top, and I feel like if that is all super cold, I feel like since the Earth is tilted at an axis a little bit, I feel like the sun, if it's right here in the Antarctica or the top of up here in Greenland, it should be really hot there. Because if the sun's over here, and it's
You mean if it's tilted that way?
Yeah.
Okay, Zeke's saying if this is the sun, and so we're tilted towards the sun, he's saying that actually at this point, the North Pole should actually be really warm. No. Not exactly, because look though, it's still ultimately up here, and the sun's rays aren't going to ever hit it directly because it's not coming at it like this. Yes, it's getting more sun now, so it is warmer at the North Pole now than it would be at winter, but it's still never going to get that direct sunlight. If I were to put my phone back on it at this angle, you would be able to see that, again, there's a nice little dot right here, but up here it's a really spread out. So it's not getting direct rays from the sun. It is getting more from the sun when it's tilted that way, but it's not getting direct sunlight.
On here, on the 180 degree thing, it shows that the light just kind of goes over it.
Well, they're showing the Earth at 90 degrees, at a perfect up and down, which we know that the Earth is actually tilted. So this picture isn't exactly accurate at the bottom of page 364 because it's not showing Earth on its axis, right?
I'm talking about the pictures on 365.
So it might be more like if this picture showed Earth tilted on its axis, it might be the sun's rays are actually hitting the North Pole at 150 degrees instead of 180 degrees. But it's never going to be hitting it at a more acute angle than that, I wouldn't think. Okay. All right. So looking at page 366, now we know how the heat is getting to us, but how does the atmosphere hold that heat in? Okay. It's like insulation. It's like that fiberglass that's in our walls.
Well, there's nothing in the ground.
So but how? So the atmosphere forms 5 layers of gases around Earth. The layer of gases closest to Earth's surface is the troposphere. We learned that yesterday.
Can you
Unpin myself? Yes.
Why?
Because I'm not even on the camera. Okay, so they can see each other. All right, so the thickness of the troposphere is greatest at the equator and smallest at the poles. Above the troposphere, we have stratosphere, mesosphere, thermosphere, and exosphere. We learned all of that yesterday. And a height above the Earth increases, the number of particles of gas in the atmosphere decreases. So they're saying the air gets thinner and thinner and thinner. There's less and less oxygen the further out you go. We talked about that yesterday as well. Talks about how far it is yesterday. We said that the exosphere begins at about 640 kilometers above the Earth's surface and ends at about 10,000 kilometers above the Earth's surface. And that makes sense because yesterday we did say that the exosphere is 6,200 miles wide. Okay. Weather happens in the troposphere. We talked about that yesterday. And it can be hot, cold, wet, dry, cold, stormy. We know all of that. But I'm going to skip. No, I'm not. Factors that affect the weather include temperature, wind, and cloud cover. When the sun's energy hits the earth, and it shows those pictures down below, 50% of that heat is absorbed by Earth's surface, and about 5% of it is reflected back up off of Earth's surface. So what happens to the rest of that energy? So clouds actually absorb and reflect some of it. So if we look at that picture at the bottom of page 366, it's showing us that I can't see what I'm doing if I don't pin myself. Sorry, guys.
Oh, that's fine.
All right. So in this picture, and you guys have it too, it's showing us the sun's rays. And again, they're not coming at us straight on, because unless we're right on the equator, those rays aren't coming straight on us. So 50% of the sun's rays, half of the sun's rays, are hitting us, and they reflect back up. But then the clouds and the other things in the atmosphere are absorbing it as well. And not only are they absorbing the direct sunlight, but then they're also catching this part that's reflected off as well. Okay. Ooh, I'm not doing a good job holding that. Okay. So they're catching that part that's reflected up as well. So that heat energy, as much of it as possible, is getting trapped. So some of it is reflected by the clouds, and we're losing that energy a little bit, but not entirely. Okay. So the air particles in the atmosphere press on Earth's surface and on all the things around. The force that they put on a given area is called air pressure. Have you guys ever heard the weatherman or whatever talking about the air pressure? Yeah. And you're like, what is that? Or maybe you haven't heard of it at all, and that's okay too. Or atmospheric pressure. And that's how much pressure, because it doesn't weigh much. It doesn't feel like I'm holding anything in my hand right now. But there's oxygen and nitrogen and all of those other gases from the atmosphere in my hand right now, right? Like if you held a balloon doesn't really weigh anything. But if I were to put it on a really good scale, a really fine scale, it would say that it weighed something. Remember when we put a balloon that had air in it and a balloon that didn't have air in it? And we weighed them, and we found out that it's little, but the air does weigh something. But think about all those layers of air in the atmosphere, and the weight does add up when you put all of that weight from the atmosphere. Okay?
That experiment we did?
That's what I just said, that experiment where we weighed the air. Okay? So the air does weigh something, and all of that weight added together from the exosphere, thermosphere, mesosphere, stratosphere, troposphere is pushing back down on the Earth. And it's a very tiny number, because like we said, we saw air doesn't weigh much, but it does apply some pressure. Okay, just like if you were to put a blanket on you, you can feel it on you, but it's not actually pushing you. Same as the gases in the air. Some days feel, and sometimes when you go outside, doesn't the air just feel heavier? It feels thicker.
Yes.
And like when it's humid outside, the air feels thicker and heavier. So you would probably say on those days, and I'm definitely no meteorologist, weatherman, but the air is heavier on those days because of the pressure from that specific type of weather. Okay. I'm continuing to read. At sea level, the average air pressure is 1.04 kilograms per square centimeter, or 14.7 pounds per square inch. You can think of this as the weight of a column of air pressing on a patch of Earth's surface about the size of your thumbnail. We don't feel this weight because atmospheric pressure pushes in all directions, and they push and balance each other out. So what they're saying on that way, I don't feel that the air is pushing on me this way, because the air is also pushing on me this way, and it's pushing on me this way, and there's even air like towards my feet pushing up on me. So the air is literally pushing at me from every single direction. So it's not like I just feel like this massive weight pushing me down towards the ground, because it's actually pushing at me from every direction. So this air is pushing me this way, but this air is pushing me this way, so it evens out and they balance each other out. Does that make sense?
You didn't have the air pushing you on top. You didn't have the air pushing on you on top, and it was on the bottom.
No. Okay. You can think of, even though air looks empty, it contains a mixture of gases such as nitrogen and oxygen. And so then it says, like, we know that because of balloons. And we already did the experiment with the balloon where we weighed an empty balloon and balloons that I blew up, and we could see that that weighed more. Okay?
Are you reading the next page?
All right. I wasn't originally, but I do want to kind of talk about this a little bit. We got time. All right, what changes air pressure? Hang on. All right, so there are lots of variables that affect air pressure. I'm on page 368 now, including volume, temperature, height above Earth's surface, and the amount of water vapor. Well, that's weird because I totally just talked about humidity, which is water vapor. All right, here we go. Volume. We've heard that word during math, probably. We will learn about volume hopefully towards later the end of this year. Have you guys learned anything about volume yet, or you just heard of it?
Well, we've heard like volume
on a
is
starter.
air. Like,
Okay. All right. Right now, volume mostly means like how loud something is to us. But volume is also a way we measure how much something fills up something. Okay. So let's talk about it. Volume is the measure of how much space an object takes up. So I could say the volume of how much fits in my hand sanitizer container. I would measure this with volume because I could measure it with height, but it's more than just height, right? It's not just a one-dimensional like height. Like I also have to take into account the width and the length and the height. I have to do all of that. So when we fill something up, we measure it by volume. How much water fits in your bathtub? We would measure that with volume. Okay. All right. Think about a container with a bag taped over it. If you pull up on the bag, you are increasing the volume because the bag is taped over the container. As you pull, more space is available for the same amount of air. The air pressure in the container decreases. Okay. So think about this, and they show the picture in the bottom. They've got just a jar and they put what looks like a Ziploc bag over it. And when they lift up the Ziploc bag a little bit, then there's more room for everything to spread out in there. So there's more volume. Okay. Somebody on pen raised their hand. Josie, yes, ma'am.
How do you like measure volume? Like, how do you say it? Like, as an example, 60. Do you just say 60 volume?
You would say volume ends up being cubic because you're measuring it three different directions. You're measuring it width, length, and height. So you would say cubic because cube, remember when we did exponents, we said if it was a little 3, it meant cubed. So cubed means 3 in math. So we would say cubic, and then it would depend on what. So like if I measured this, I wouldn't measure it in feet because that's 12 and that would be too, but I might measure this in centimeters. So I would say the volume of this is, I don't know, cubic centimeters is how you would say that. So if I got a ruler out and I measured how many centimeters tall, how many centimeters wide, and how many centimeters long, I would multiply those three numbers together. We'll learn that later. And then I would say it's 60 cubic centimeters or whatever it ended up being. Does that make sense, Joe? Okay. Good question. Okay. So do you guys understand that first picture on the bottom of your book? This is what they're talking about. If you raise the bag up, then it's going to have more volume because there's more area for those molecules in there to spread out. I don't know what's happening, but stop it because whatever's happening is distracting a bunch of, because I see everybody looking over here instead of at me. So stop. Okay. Okay. So the air outside, I'm going to fast forward to temperature. Air pressure also depends on temperature. When air is heated, the gas particles speed up and spread out into a larger space if it is available. There are now fewer particles of gas in the original space. The air pressure decreases and the air weighs less. So when it is hot, as air temperature increases, the pressure decreases. So if you look at that second picture at the bottom, in the regular temperature jar, you see that the molecules are all really close together. I remember in 3rd grade, didn't we do something where we talked about if it was cold and then if it heated up, and I had you guys like bouncing off of each other. Did we do that?
Yeah.
And I put like maybe hula hoop on the floor and had a bunch of people, and I was like, okay, this is cold, this is warm, this is hot, and we spread out. Well, in my room we did that, I'm pretty sure.
I was in your class, but
maybe you were absent that day, but we definitely did it. So the warmer it gets, the molecules spread out. And so they're not pushing on each other as much. So kind of like how we do our classroom with coronavirus. I could put 4, 5, 6 people at a table, but then we would be really packed in tightly. And that, right. And we don't want our germs all on top of each other. So we spread out as much as we can. So that's why we're saying stay 6 feet away so that our germs aren't all on top of each other, breathing each other's same air, right? We spread out. And just like that, when it's the warmer it is, the molecules automatically in the air, the gases in the air automatically like spread out. So they're not pushing as much because they're spread out. Okay, height above Earth's surface. The column of air above a mountain is shorter than the column of air above sea level. So if you think about this, remember I talked about like, so there's weight pushing down. So the higher up I am, there's not as much air above me to push down.
Is that why we can't jump as high?
Does that make sense? Yeah. So the lower elevation I am, there's a lot more atmosphere on top of me. But if I go up to the top of Pikes Peak, mountain in Colorado, there's not as much air above me. There's not as much atmosphere above me because I'm already several 100,000 feet in the air. So now there's not as much atmosphere to press down on me. So there's less pressure the higher you go. Okay. And then the amount of water vapor. So we talk about water vapor in the air is humidity. I know you guys have heard people talking about it's humid outside. And that's what it feels like. It's just like you go outside and it feels like wet and it's hot and sticky feeling outside. And that's because there is water vapor, which is water gas and water in gas form in the air. There's more water molecules in the air. Air is a mixture of gases. Water vapor weighs less than most of the other gases in the air. When water vapor is added to the air, the mixture of gases becomes lighter and it exerts, which means presents less pressure than dry air. Humidity is the amount of water vapor in the air. Okay. All right. Tomorrow, and I sent a message to virtual friends, I believe, to you and your family. And I sent a message to you guys' family this morning. Some of you already brought them in. But if you haven't already, you guys bring in a Walmart bag. I think some people brought extra, so I think I have enough. But I also am supposed to be providing it for like other classes. And then you guys at home, tomorrow we're going to do an air pressure experiment. And I want you guys to have like a Walmart bag. I guess it doesn't have to be Walmart. It could be Schnucks or whatever, but you know, like a grocery shopping bag. And then you're also going to need a sharpened pencil, and you're going to need a cup. It can't be like a little Dixie cup. It needs to be like a pretty decent sized cup or a jar. Something like this would be okay. I have this little decorative jar on my desk. Did Riley give me this? Somebody gave me this. I don't know. Grace, yes, ma'am.
Well, like a glass cup.
Yeah, that would be fine. In here, they're going to have those like red Solo cups that we sometimes use for stacking, or you can use them for drinking or whatever. We're going to use those in here. If you guys need a Walmart bag or a pencil or a cup, I mean, I feel like that's something that most people have at home. But if you guys need that, let me know and I can have it ready for you guys to pick up either later today or tomorrow. Okay, we're going to stop there for now.
What do we have next? Recess.
Hang on, no. I have a video I'm going to show you, so don't leave yet. Don't leave yet. Okay.
Is there on this?
Now. Yeah, Josie.
Do we have a worksheet for today?
There is no worksheet for today, but we're going to watch a fairly quick video. You guys heard of Bill Nye?
Yes.
Bill Nye, the science guy.
Guess what? He was on the Masked Dancer.
He's been around for forever.
Yeah, I
Bill Nye,
know
the
how he
science-
died.
Well, I don't know why there's a bunch of
He
people
didn't
talking.
die. He's still alive.
He's not dead.
Yeah,
He has a new
was
show on
just
Netflix.
Masked on the Masked Dancer.
Oh, yeah.
Yeah.
Do you want me to bring in our bags for Miley?
I was thinking of somebody else.
You can. I think I have. I think I have. Plenty. Well, let me check here in a second. Atmos. I cannot spell atmosphere. Okay. I'm not sure why there's so much talking. Chill. All right. So Bill Nye, the science guy. He is a real scientist.
He's a really great dancer.
And He has been doing experiments and teaching science to kids for forever, since I was a kid. He's still doing that now today. He's got a show on Netflix currently, but he has had a show on different channels for years and years and years. And the episode we're about to watch is a really quick experiment he does with air pressure. And it's not one of his newest shows. It's a little bit older. So hang on just a second and I will present this.
Is it from 19 something?
I don't remember.
Most likely.
Probably. Yep.
All right, let's see here. Present.
It's made. Well, how long?
my brother
Tab. Bill Nye. Let me go back and mute. Okay, you guys have to stop talking. Okay. All right. Hang on 2 seconds. I gotta mute myself so. All right, so hang on, sorry. Pay close attention to what he is doing. I'm not going to say anything about it up front, I don't think. Hang on. Okay.
I think you gotta move the camera towards it.
All right. So I will. So Bill Nye, this is Bill Nye. It says the air that surrounds the Earth is called the atmosphere. We know that. He says that compared to the size of Earth, the atmosphere is very, very thin. It's made from gases, mainly nitrogen, oxygen, and water vapor. But it also has little bits of other elements called argon, carbon dioxide, xenon, neon, helium, and sulfur. The atmosphere does a lot for the Earth. It blocks the ultraviolet light, burns up the meteors, traps in the heat, and it has our weather, keeping us wet with rain. Okay. If we could fit the atmosphere, the entire atmosphere, on a scale, it would weigh 5.6 million billion tons.
How does he know that? Who scaled it?
They can measure a section of it and know how much that weighs. They can measure, okay, this much of the atmosphere weighs this, and then they multiply that by how big the atmosphere is. Okay.
Million.
Okay. All weather's made in the atmosphere, and hailstones form in the atmosphere from layers of snow and ice mixed together. Okay. Where did he learn this from? Check this out. Here are some research books that he read that helps him learn more. So, like, these are his sources that he's citing. This is where he learned about the atmosphere. This is called The First Book of Air, A Basic Guide to the Earth's Atmosphere, and How Did We Find Out About the Atmosphere? Okay. Those were written by other scientists long ago in 1961 and 1985.
Where did they get the information from?
Okay, I don't know. All right. All right, so here we go. Bill Nye and the atmosphere.
Bill Nye the Science Guy. Bill Nye the Science Guy.
If mountaintops are closer to the sun, why is it always colder up there than it is down here in the city? Well, please consider the following. Our atmosphere is thin, but it's thick enough to keep us warm. Now, when you're wearing a coat like this one, it keeps you warm because it holds air next to your body. The same thing with the atmosphere. There's more air above us when we're down here in the city than when we're way up here in the mountains. So it's like the world's low places are wearing more coats. They're wearing more air than these places up high in the mountains. Now, as you travel up through the atmosphere,
Did that make sense to everybody what he was saying? That the atmosphere, literally how our article yesterday said, is like a blanket keeping us warm. You would think the mountains put you closer to the sun, but it's the opposite. You don't have as much of your atmosphere blanket on when you're up there, right? Do what, Max? So what he was saying, look at this again. When he had that mountain, the higher up you go, there's less atmosphere because you're further up, right? So being up on the mountain, then there's less atmosphere, which means you're wearing a jacket, not a coat.
Oh.
Like an atmosphere jacket, not a coat. Does that make sense?
Yeah.
Okay. So when you're down on the ground like we are and we're not on a mountain, there's a lot more atmosphere around us. And so it's like we're wearing a coat, not just a jacket. So to say, like the earth is wearing a coat, not a jacket. All right.
It gets colder and colder as the air gets thinner and thinner until you're up around 10 kilometers. That's when you leave the troposphere and enter the stratosphere. Anyway, the rate at which it gets colder is called the lapse rate, and it's about 5.5 degrees Celsius per kilometer. So thinner until you're up around 10 kilometers. That's when you leave the troposphere and enter the stratosphere. Anyway, the rate at which it gets colder is called the lapse rate, and it's about 5.5 degrees Celsius per kilometer. So a mountain, say 3,000 meters high, let's see, that's about 10,000 feet, would be about 17 degrees Celsius colder than it would be down here in the city. And that's plenty cold enough for there to be a spring shower in the city while it's snowing up in the mountains. Thank you for joining me on Consider the Following.
Bill Nye the Science Guy.
Oops. All right, so does that make sense to everybody what he was talking about? It's colder up on the mountaintops. There's less atmosphere up there, and the atmosphere again is trapping all of that heat. So if there's less atmosphere up high, remember if you think about our poster yesterday, the troposphere is this thick. So the mountain, the earth might be here, but a mountain's going to be up here, so there's less troposphere above to keep you warm, okay? And so it's colder up on the top of the mountain. That's why mountains always look like they have snow on them, even if it's not snowy at the base of the mountain. The whole time I was in Colorado, it was June, I think, and when I was at the top of the mountain, there was snow everywhere.
I want to go on a mountain.
Yeah, it was pretty cool. I'll have to see if I can find some pictures to show you guys of when I was on the mountain. But anyway, okay. So I just want to show that little video because I think it gave you a little bit more information about the atmosphere. There is no worksheet for today. It was just discussing and talking. So that is all I have today. Another atmosphere Kahoot. What I can see if I can find another atmosphere Kahoot for you guys. Give me a second.
This should be like our thing to do every single day.
Every single day, just do a Kahoot at this time.
A lot of people left though.
A lot of people left though. Well, I don't know, and obviously this isn't for you guys because you guys are still here on the call. But if anybody happens to be virtually watching this recording back, I'm not sure why everybody keeps bailing on all of our calls, like watching them for 5 minutes and then you guys leave.
They don't even watch the recording because they think they know everything already.
I'm not really sure what's going on there, but this is your school. You're supposed to be here.
Thank you, Josie, Grace, and Cam.
Yeah, thank you, Cam, Josie, and Grace for being here and doing the job. Okay.
Yeah.
All right. Oh no, you can leave the lights off if we're doing Kahoot. Let me find one.
I can be irresponsible. Spend $6. Oh my God.
I am not spending money on Kahoot. You don't need to. It's free. Atmosphere.
She's not ready yet. Oh, bunnies! Oh, bunnies are so adorable.
I'm not really sure why all the pictures are bunnies.
But they're cute though. Yeah, they're cute. Come on, just do it. Wait.
We didn't study some of these. Some of these you guys are going to have to guess.
Okay.
You okay with that?
Yes. Just getting time. I'll try.
Miss Bab, is it okay if I don't play? I'm just on watch.
I don't care. Hang on, let me present.
Oh, come on. Thank you. That's my brother. Hey! Okay. I don't know the last two numbers. Kendall, are you
All right.
really in?
You got just a minute to get in.
Dang, I didn't finish your name.
My name is 391. That one was serious.
I was gonna do that one dog season, but it's not
Mystery man is there. Hello,
Atmo.
All right, is everybody in?
Yeah.
5, 4, 3, 2, 1.
Time. That's my name.
Atmosphere. Wait, here we go. What's the quiz?
What is a button? Yes.
Plentiful, like which is the most?
Did we all get it wrong?
I feel like it said oxygen, right?
Yeah, I thought it was oxygen.
Nobody
So nobody got any
Where's Maggie? Jason's on the podium. I'm on the podium.
I'm on the
Maggie's on the podium too. I'm in second place.
That one dog.
Might be wrong.
What?
Oh yeah, we did talk about this.
Wait, what are you?
I like the bunny.
I was just thinking the same thing.
I think I know it. I've seen it on TV.
Oh no.
I missed failure. We're all failures.
I'm in fourth now. Mason, Lily, and Riley got it right.
And Riley.
Yeah, Lily and Riley, and then the other Riley and Mason. What?
What blocks UV? Just focus on that. What's the thing that blocks UV?
Easy. I missed like.
Ozone is the thing that blocks the UV. Ozone. The ozone is part of the stratosphere, but the ozone is the thing that blocks the rays. But that was kind of a trick. Those of you that put stratosphere, the ozone is in the stratosphere, but it's not the entire part of it. Oh, good luck. Did it say this?
No.
We don't know this one. Happy guessing.
Chromebook is
I know it.
I think I know. Me too! Yes!
Way to go.
I'm second place. How do I have Lily and Riley?
Oh, you guys know this one. You know.
What's in the middle?
Which one of these is middle? Mrs. Krusmark will be proud. Yes.
Lily and Riley. I can see Lily and Riley from behind.
Uh-oh. I know it.
Remember why the layers are named what they're named. Which layer is constantly changing because of the weather, and where does the weather live?
I know, but now I'm in 11.
I know this one.
I don't know.
Oh.
What is
No, what?
What is it?
Yeah.
This is just a guess.
Because it's where the gases are thickest, where we're breathing at.
I remember where it said in the book. Even though it's the smallest, it has the most gases.
It's got. These cahoots can also be educational, right?
Yeah.
So listen, 90% of all the gases in the Earth's atmosphere, troposphere, that's the layer we're in right now, because it's all that's all the oxygen and everything we're breathing. The gases need to be here because we're the ones that really need it. They need to be closest to us.
Let's go. Down the podium.
Shifty.
I'm the first one.
I was second.
I know it.
Oh wait. I put the one I don't know.
Yeah, okay.
I put the one I don't know.
No, it is the
Meteors. Meteors, mesosphere. They both start with M. You can remember it that way.
Yes! Yeah! I'm ancient Egypt!
Oh, careful. You know this one. You know this one. Cute bunny face.
Oh wait, no! I chose wrong! I was a light.
I got it.
I'm ancient Egypt! Yes!
There you go. Good job.
Still on the podium! You're behind me.
Oh, we just learned this today. Dense means like tightly packed together. So is it more tightly packed together
More
or
tightly packed together means less air. Spread out means more.
dense means smushed together? So do you want it more squished together or less squished together?
I don't know.
Less dense. Dense means packed together, so less packed together.
Oh, I know why.
Calm down. Just gotta stay on the podium.
Thanks, Fiona. Thanks, Kendall.
I'm on a roll.
I just have to stay on the podium.
Come on, Chicky.
Last question. This is the layer that we didn't learn about. We're going to research this here in a second.
Really? I think the one that we haven't learned about.
Yeah, we're going to figure this out here. All right. We'll look at the podium and then we're going to figure out what this ionosphere is because I'm curious.
Who's so we do another one? I'm not. This is the first time I've ever been on the podium when we played the
Three, 2, 1. Yeah!
Is that you, Kendall?
Yes!
Awesome job.
Can we do another one?
All right. No, we're going to find out what the,
I was silver.
we're going to figure out what the ionosphere is.
I was.
That was so much fun.
Layer of the Earth's atmosphere that contains a high concentration of ions and free electrons and is able to reflect radio waves. It lies above the mesosphere.
So the northern line?
No. No. And extends 50 to 600 miles above the Earth's surface. Hang on. So above the mesosphere. So it's part of the thermosphere. Hang on. Okay, so look at, it kept asking us about the ionosphere. So look here at this image, guys. It shows the layers that we know about: troposphere, stratosphere, mesosphere, thermosphere, exosphere. Okay. And then it shows the ionosphere, which is the thermosphere and exosphere together. And because of the gases in that area, that's where the radio waves, like, so when you radio somebody or whatever, the radio waves actually bounce off of that part of the atmosphere. So the radio waves just don't like go off into space. The radio waves are like walkie-talkie type stuff, or like, you know, like you turn the radio on in your car. Where did that come from? Like you,
Where did it come from?
the ionosphere. the ionosphere, which is the thermosphere and exosphere together. And it's because of the gases that make up those two layers. They reflect the radio waves back to Earth so that we can have the radio or walkie-talkies or things like that. Okay. All right. Now we've learned extra. So that was a little extra for those of you that are still on the call. Yay for you. Okay. No, it's about time for recess for us. So we're going to peace out. We will see you tomorrow for our experiment and possibly another atmosphere video.
Bye.
Bye.
Okay. Bye, guys.
Bye.
Why are you in my space? I don't have my mask on. Go away.
Social studies.